Uh, bear with me, just trying to figure this out. Zoom sometimes acts up. Let's see if this works. Are you able to see it?
Yeah, clear.
Perfect. Okay. Let me move to presenter view so I can go ahead and control this. You're still seeing you're not seeing the presenter view, right? You're seeing the actual main screen.
Yeah, we see the main screen.
Perfect. Thank you. That lets me control that easily. All right. Thanks for the invitation, Harsh. So today we'll talk about probabilistic forecasting in Python, as the title says. I'll focus on, during this presentation, I've assumed that we're coming in with minimal background in probabilistic forecasting and just a tiny amount of background in forecasting. If you have no background in forecasting in general, that's okay too. We'll start from the basics. This session is divided into two parts. We have a slide deck, which I'm starting with right now, and followed by a live Jupyter notebook. I've shared this with Harsh. Maybe he can upload it here. Let's move on to the next slide. Well, like they say, the best place to start is at the beginning. So let's look at our agenda for the day. I've structured this presentation assuming that most of us, like I mentioned, have little background in forecasting and perhaps no background in probabilistic forecasting. So we're going to build up our knowledge really from the ground up. We'll begin with the fundamentals, why forecasting is important across various fields. And this will set the stage for our main focus today, probabilistic forecasting. Next, we'll explore why probabilistic forecasting has gained such prominence. We'll discuss its advantages over traditional point forecasts and why it's becoming increasingly relevant in today's data-driven world. From there, we'll delve into the various types of probabilistic forecasts. And this diversity, it's essentially key to understanding how probabilistic forecasting can be applied in various scenarios, and it's beneficial to stakeholders at various levels. Once we have a solid theoretical foundation, we'll move on to practical methods for implementing probabilistic forecasting. I'll introduce you to some key techniques, of course, keeping the technical details accessible. Well, of course, in creating forecasts so far is only part of the story. We'll then move on to how to evaluate these forecasts, which is a critical skill for anyone working in this field. How do you know if your forecast is good? If it's bad, do you need to work on it? Can you present it to someone? All of that is very crucial. Finally, we'll round off with an overview of the Python ecosystem for probabilistic forecasting. This will give you a roadmap for further exploration after our session. As you can imagine, it's a limited session and we'll only be able to cover so much. I've designed this presentation and the notebook such that you can just take it and run with it and try new things if you so desire. Okay, all right, let's begin. By the way, Harsh, I've minimized my Zoom session and I'm on the presenter view for the slide deck on my computer. So if something goes off in the presentation, I'll be unable to tell. So just please unmute yourself and let me know, okay?
Yeah, sure.
All right, appreciate that. Well, let's start with motivation, right? Let's kick off things by talking about why we are focusing on time series data in the first place. You might be wondering why all the fuss about time series, why this presentation? It is a big deal and it's getting bigger by the day. So I've pulled some stats. So the first one is a stat from Timescale. What they're really saying is the amount of time series data being stored by organizations has skyrocketed. We're talking a 15-fold increase in just 3 years. That's not just growth, that's explosion. If VCs could invest in it, they would be all over this. Now next, let's look ahead a bit. IDC, which is a major player in market intelligence, they're predicting that by 2027, which is really around the corner, nearly 30% of all data is what they call the global data sphere, will be real-time data. Now think about that for a second. Almost a third of all data will be time-stamped, continuously updating information. That's huge. And if you know how to deal with it, that'll give you a huge advantage. Influx Data did a survey last year, and they said 78% of the folks that they talked to said they're dealing with more time series data now than they were just a year ago. So more than 3/4 that responded, they saw an uptick in time series data management. And I put that figure to the right, that little cityscape, to demonstrate that how the tower dominates the image. So that's a visual metaphor for how time series data is becoming a massive part of the data landscape. And it's like this looming presence that we can't ignore anymore. The point is, time series data, it's here, it's going to get bigger. And I know a lot of data science community focuses on images and videos, and even sounds and natural language processing, which is fantastic. But time series data, it's here, it's going to get bigger, and we need to learn how to work with it. Next slide. Now that we understand why time series data is so important, let's talk about what we actually do with it. This brings us to forecasting. Let's start with what forecasting is. In simple terms, it's our best shot at predicting the future based on what we know from the past and from the present. It's kind of like being a detective, but instead of solving past crimes, we're trying to figure out what's going to happen next. We use historical data, we use current trends. Think of this as learning from experience. Forecasting isn't just for weather forecasting, right? You have weather apps on your phone. It applies to all sorts of fields, and we'll cover this. It applies to economics, business, public health, you name it. Anywhere you find patterns over time, you can probably use forecasting. And here's where it gets interesting. It's not just about crunching numbers. Sure, we can use science and data analysis, but there's also an element of intuition involved. It is part science, it's part art. And why do we bother with all of this? Because it's essential for planning and decision making. Whether you're a business owner trying to manage inventory, whether you're a government official planning public health measures, good forecasts can make all the difference. The monkey in the corner, I actually generated that using Midjourney. Yeah, that's like the cute clip art. It's there to remind us of something crucial in general, and particularly regarding this presentation, uncertainty. No matter how good our models are, how much data we have, there's always going to be some level of uncertainty in our forecasts. We're dealing with the future, after all, and if there's one thing we know about the future, is that it can surprise us. So remember, while forecasting is incredibly powerful, it's incredibly useful, it's not about predicting the future with 100% accuracy. It's about making the best informed decisions, given the information that we have on hand. Why forecasting? We talked about why time series, what is time series, why time series, what is forecasting, and now we need to motivate why forecasting is relevant in different domains. Let's take a moment to consider the different fields in which the different real-world applications, right? I have a collection of icons here. Each one represents a different domain where forecasting plays a crucial role. I've got weather, I've got finance, I've got energy, I've got healthcare, retail, transportation, climate, agriculture, and these are just the ones I could fit on here. The key takeaway is that the sheer diversity of these applications, it's just mind-blowing. Forecasting isn't one field or any one industry. It's a versatile tool that's applied across numerous sectors of our society. And this wide range of applications, it underscores a fundamental point in that forecasting is essential for planning and decision-making in almost every aspect of our lives. Over the next few slides, I'll delve deeper into each of these domains. But for now, just what I want you to appreciate is the breadth of forecasting's impact. Weather and climate, and I'm like a very empiricist kind of person, so I like to motivate things by taking very specific examples. Where can forecasting play a role in weather and climate? Meteorologists can forecast a sunny weekend, which will maybe encourage you to go plan an outdoor event. They can forecast a mild winter, if you're talking about long term, which will influence energy companies' fuel stockpiling decisions. Finance and economics. Analysts forecast 2%, 3% GDP growth, which will guide government budget decisions. A company can project 10% sales growth, which will inform their future expansion plans. Energy. Grid operators can forecast peak summer demand to plan power generation. Wind farm developers, they use wind speed forecasts all the time to estimate energy production. Healthcare. Hospitals forecast patient admissions to plan staffing levels. And we all know how important this was during COVID. Same thing, health authorities, they predict the flu season severity to plan vaccine distribution. Retailers, they forecast holiday season sales to manage their inventory. And just something that comes to mind are the toilet paper shortages during COVID, right? E-commerce platforms, they predict Cyber Monday traffic to prepare their server capacity. In transportation, airlines forecast passenger numbers to plan flight schedules. And when these go wrong, we all know how frustrating it can be if a flight is overbooked and then, they bump us. So forecasting is like, it can become very personal. Shipping companies, they predict delivery volumes to manage their fleet size. Disaster management. I live in Florida and it's hurricane season here. Emergency services use hurricane path forecasts to plan evacuations. Forest services out, say, in Oregon and California, they predict wildfire risk to allocate firefighting resources. Agriculture. Farmers use growing degree day forecasts to plan planting dates. Fruit growers, they predict harvest times to arrange their labor and distribution. So, and I just took two examples from each of these 8 fields, and already you can get a sense of how extremely critical it is to forecast and how critical it is to forecast right. Okay, if forecasting is good, then why do we need probabilistic forecasting? All the things that I mentioned earlier, they were point forecasts or deterministic forecasts, if you will. They don't always answer all the questions that you need for making decisions downstream. So out of the 8 domains that I picked to save space, I put in 3 here. If you look at the weather and climate, right, first column. If, let's say, let's look at scenario B. Seasonal forecast, they predict a wild winter, thus influencing energy companies' fuel stockpiling decisions. This is something we covered. What if we could also provide probability distributions for winter severity, which will enable more nuanced energy resource planning? What if we could forecast the likelihood of an extreme cold snap, allowing for better emergency preparedness? For those of you who are based here in America, this happened not that long ago in Texas. There was a cold snap. They weren't really prepared for it, and several people ended up getting utility bills worth thousands of dollars. So So this is why deterministic forecasting has its limits, and we need probabilistic forecasting. Same thing with finance, right? I said analysts forecast a 3% GDP growth, which is great. But what if we could provide a range of GDP growth scenarios with associated probabilities, which allow for a little more robust policy planning? What if we could forecast the likelihood of a recession, enabling more proactive economic measures? I mentioned a company projects 10% sales growth, thus informing their expansion plans. What if we could also give probability distributions for sales outcome, which could help the company provide a plan for various scenarios? What if we could forecast the likelihood of market disruptions, informing risk management strategies? And we can go on and on and on, just various what ifs, which are not satisfied by point forecasting decisions. You need probabilistic forecasting. Okay, let's dive into this flowchart just to summarize what we've seen through all these examples. At the top, we have probabilistic forecasting, which is our risk assessment. This is the secret sauce, right? The whole point of probabilistic forecasting is to allow risk assessment. It's not just about financial risks, to be clear, or like market volatility. It's an umbrella term. It's crucial when we're talking about climate change models or predicting the outcomes of a new drug trial. It's all about understanding what could go wrong or what could go right, hopefully, and how likely each scenario is. When we move down to decision-making, resource allocation, and scenario planning, these are all, again, also universal. Whether you're deciding on a product launch, you're choosing which experiments you run in your lab, you're using the same principles, basically. You're asking, where do I put my money? Where do I put my time? Where do I put my effort? And you're playing out these different scenarios in your head. Okay, now see where these lead, right? These lead to improved accuracy, efficient operations, and enhanced preparedness. In business, this could mean more accurate sales forecasts. It could mean a smoother supply chains. In science, this could mean refining a climate model or even optimizing a particle accelerator. The goal is the same: do things better and be ready for what's coming. All of these, they funnel down to better outcomes, like we mentioned. In business, that could be about the bottom line. It could be about profits, market share, customer satisfaction. In science, it might be about groundbreaking discoveries, successful experiments, or securing the next round of funding. And at the very bottom, of course, we have competitive advantage. I mentioned at the very beginning that time series data is exploding. It's going to encompass a significantly larger percentage of all data. Just knowing about it gives you a competitive advantage. And this is not just a business thing, but scientists are also competing, right? They're competing for publications, grants, the first to make a big discovery. It's all about staying ahead of the curve. And this is where we have the beauty of probabilistic forecasting, is that it gives us a framework to deal with uncertainty, whether we are in the corporate world or academia. It allows us to make smarter decisions about being prepared, and ultimately about pushing the boundaries of what we can achieve. Okay, that's a whole lot of motivation. Let's get down to some dirty equations, right? We'll start with what simple point forecasts are, which is something most of us are familiar with. Don't let the equation scare you. If you're not familiar with the notation, we'll break it down into simple terms. A point forecast is exactly what it sounds like. It's our single best guess about what's going to happen in the future. Though it's like the weatherman saying, tomorrow's high will be 75 degrees Fahrenheit. And I apologize to my non-American friends. We use freedom units in America here. So 75 Fahrenheit is a point forecast. Why is that important? Well, point forecasts are really the bread and butter of many decision-making processes. It's the type of forecast that most of us, if not all of us, are familiar with. they give us a concrete number to work with, which can be really helpful when planning decisions. If you look at the graph on the right, it's simply the orange line, which is our forecast, trying to follow the blue dots, the actual observations. It's as simple as that. What's missing here, and what's crucial, is that point forecasts have a limitation. It's something we've covered, the benefit and really the importance of probabilistic forecasting. Point forecasts don't tell us about uncertainty. It'd be like saying, if you threw a party and I was like, sure, I'll be there at 9 p.m. or something more important. You were supposed to meet a friend and you're like, okay, I'll be there at 3 p.m. That's great. But what if there's traffic? Your friend is just waiting there for you and you didn't give them a range. A point forecast doesn't capture that kind of uncertainty. As we've seen in the real world, in power generation, in economics, in retail, we might use a point forecast to estimate how much power we'll need to produce at a certain time, how much we expect to sell. It's useful, but it's not the whole story. Which is why we move on to probabilistic forecasts. Okay, let's talk about something more sophisticated, the types of probabilistic forecasts. I hope so far I've been able to convince you that why forecasting is critical, why point forecasts are absolutely great, but they are limited. And hence we need to incorporate probabilistic forecasting in the type of forecasting we do, period. Here's where we kind of get technical. We break down probabilistic forecasts into these 4 bins. Instead of giving just one number, of course, probabilistic forecasts will give us a range of possible outcomes. First, we start with interval forecasts. Think of interval forecasts as just giving us a range, like saying tomorrow's temperature will be between 65 and 75 degrees. That gives us a good upper and lower bound, which is already more informative than a single point. Then we have quantile forecast, which is a bit more higher resolution. It's a bit more nuanced. It tells us about different percentiles or quantiles of the forecast. For example, we could say there's a 25% chance the temperature will be below 68 Fahrenheit, a 50% chance that it will be below 72 Fahrenheit, and so on. So it just gives us more detailed picture of the possibilities. Distribution forecast. This is like the full Monty of probabilistic forecasting. We're looking at the entire PDF of possible outcomes. It's almost like having a complete map of all the possibilities and their likelihoods. And then finally, we have scenario forecasting. This is where we consider different possible futures or like what-if scenarios. It's particularly useful when we're dealing with complex systems where different factors could play out in various ways. So if you're familiar with, say, or if you've even heard of Monte Carlo simulations, they would fall under scenario forecasting. Hirsch mentioned a library that I created, TS Bootstrap, where it's a specific library for time series-based bootstrapping. That would fall under scenario forecasting, and we'll, of course, cover this later. Okay, let's delve into interval forecasting, and then we'll slowly work our way all the way through, all the way to scenario forecasting. Okay, an interval forecast it provides a range, like we mentioned, within which an expected future value will fall with a specified probability. I like taking temperature examples because they're easy to explain. So it's like, instead of saying that tomorrow's temperature will be exactly 75 Fahrenheit, we might say that it'll be between 70 and 80 Fahrenheit with a 90% confidence. The equation here, it defines this interval with lower and upper bounds based on the quantiles of your PDF. The alpha value there, it represents the confidence interval. So in this temperature example that I just mentioned, I said 90% confidence interval, so which means alpha was 0.9. Looking at the graph, the gray shaded area represents these prediction intervals, and the red line is our point forecast. That's like saying exactly 75 Fahrenheit prediction. while the blue dots are observations as it's visible in the legend. If you notice the gray line, it slightly widens from left to right, not too much, but noticeably. This is an important point. This illustrates increasing uncertainty as we forecast further into the future. So if you assume that 0 is time now, and we start forecasting from t equals to 1, which is like 1 unit ahead, all the way to 40 units ahead. It's like predicting the weather. We're more confident about tomorrow than we are about next week.
Sankalp, yeah, may I bother you for a second? There is a question.
Yeah.
What is the difference between prediction interval and confidence interval?
Oh, that is a fantastic question. It might take me a while to explain it. Could I come back to it later? I'm glad you asked. Yeah, okay. That's a really good question. Thank you. I just want to be able to get through the presentation, that's all. I'll come back to it. I was talking about alpha, right? The choice of alpha. We said 90%. It gives us a higher alpha, gives us a wider interval with more confidence, but as you can imagine, with less precision. A lower alpha, it's like saying the temperature tomorrow will be between 73 and 77, which is good. We get more precision, narrower range, but now we are less certain of capturing the actual temperature. Interval forecasts, when people start moving from from point forecasting to probabilistic forecasting, interval forecasts are usually the first type they go with because they are easy to understand and they're valuable across a number of fields. In weather forecasting, they help people plan activities, acknowledging that there is some uncertainty. In financial markets, they inform investment strategies. They offer a more nuanced view of the world than point forecasts, but not as nuanced as quantile forecasts, which is what we'll be moving on to next. Okay. Quantile forecasts are honestly my favorite types of forecasts. They are a powerful tool in the probabilistic forecasting toolkit. They give us specific threshold values at different probability levels. So imagine asking, what's the maximum temperature we can expect with 90% confidence? So that's where a quantile forecast would come in. If you look at the equation again, if you're not familiar with the notation, just don't be intimidated. In plain English, what it's saying is that the probability of our future observation y being less than equal to our quantile forecast S is equal to the quantile Q we choose. If you're looking at the 90th percentile, there's a 90% chance that the actual value will be below our forecast, or at least that's what the model is telling us. There are more nuanced issues about calibrating the model, actually assessing its predictions with real data, but that is what the equation is telling us. The second part of the equation, it shows how we calculate this forecast using the inverse of the CDF, or the cumulative distribution function, which is the F's hat inverse. It's the mathematical backbone that generates those quantile lines that we see in the graph. Speaking of the graph, by the way, let's look at how these quantile forecasts play out over time. So I've used different colors for different quantiles. Each represents a different quantile from the 10th to the 90th percentile or quantile. The space between, say, the 10th and the 90th percentile lines, that's your 80% prediction interval. It's as simple as 90 minus 10. Why is this useful? Quantile forecasts are particularly handy when being wrong in one direction is more costly than being wrong in the other direction. I mentioned earlier, like planning an outdoor activity, right? Let's carry that example forward. You might be more concerned about it being too hot than being too cold, just based on where you live or what kind of temperatures you like. In finance or energy, these forecasts can help plan for different scenarios. Lower quantiles might represent conservative estimates, while higher quantiles could be more optimistic projections. I mentioned earlier they are one of my favorite methods of probabilistic forecasting. It's because of their flexibility. They are particularly valuable when we're dealing with non-normal distributions on where or when we are interested in specific probability thresholds. And of course, they complement other probabilistic forecasting methods, which we'll cover in the next couple of slides. Just like with interval forecasting, probability quantile forecast, the lines, if you notice from the middle to the right, they kind of fan out. Same idea. We are less certain about the distant future than we are about the near future. That wraps up quantile forecasting. Just any questions, absolutely happy to answer. Just let me get through the slide deck. Let's talk about distribution forecasts. This is where things get, this is like big boy forecasting. This is where things get interesting. We're looking at the full picture of what might happen in the future. One way to think about distribution forecasts is like the Swiss Army knife of probabilistic forecasting. Instead of giving you a single number, instead of giving you a single range, we're mapping out the entire landscape of possibilities. It's like having a weather forecast that doesn't just tell you that it might rain, but it gives you the odds for every possible weather scenario. If you look at the equation there, that's the heart of our distribution forecast, where omega, it represents our future value. Where t is the current time and k is like the horizon at which we're looking. The tilde symbol is the as distributed as or distributed according to symbol. And f hat right at the bottom, it's our PDF. So what is this density function really? It's essentially our best guess at how future values will spread out. It's a sophisticated mathematical way of saying, here's how likely each possible outcome is. So we can walk through the entire equation in detail, but I would rather not do that just for sake of time. The integral at the very bottom, that's showing us how to calculate the CDF from the PDF. It's a very common equation. I'm sure several of you might be familiar with it. Why is all of this mathematical machinery useful? Look at the graph to the right. The shaded area, that's the distribution forecast in action. The darker areas represent more likely outcomes, while the lighter areas obviously are the less likely outcomes, but still possible scenarios. It's kind of like a heat map of the future. Just like with quantile forecasts, distribution forecasts are very flexible. You want to find the most likely scenario, you just look at the PDF or at a given X or a given time. Just like, I've sort of put an inset figure there. And voila, at any given time, you have the entire range of possible outcomes. That is a distribution forecast. Any questions, definitely please make a note and we'll come to them later. Finally, pardon me, we'll move to scenario forecasting. This is where things get interesting because we're mapping out like multiple possible futures. Imagine you're planning a road trip. A point forecast might tell you your estimated arrival time. But scenario forecasts, they're like having several alternative routes mapped out, each with its own twists and turns, like in Google Maps. You can ask it to avoid highways. You can ask it to avoid tolls. So just like a couple of examples off my head, those are different scenarios, that different paths you might take. I have an equation here where eta represents the ith, eta I is the ith scenario, and sigma is our estimated multivariate PDF. It's like the big picture of all possible outcomes. The graph, each of those gray lines, each is a potential future path, and blue, as we've been following so far, the actual observations. What makes scenario forecasting powerful is that they capture the complex interplay between different variables. In power generation, for instance, we might be looking at demand, at weather patterns, at equipment availability all at once. And there's a covariance matrix there. It's like juggling multiple balls. Scenario forecasts help us see how all of these quantities might evolve together and how that might affect, say, the demand for power in the future. That wraps up scenario forecasting. However, as you can imagine, we've been going from simpler to more and more complex forecasting. There are challenges when it comes to communicating these scenarios. It can be tricky. Not everyone is comfortable in thinking in terms of these multiple future paths and deciding how many scenarios to generate. That can often be a decision that a data scientist or a forecaster might need to make and then explain to their stakeholder, and that can be tricky too. But in my decision, or in my opinion, for decision makers, the benefits will outweigh the challenges like 9 times out of 10. They allow us to prepare for different possible outcomes, assess risks more comprehensively, and make more robust decisions. Now that we've covered the types of probabilistic forecasting, what are the tools that we'll actually use for this purpose? We've got 3 different, you can bin these models into 3 different types, statistical machine learning and deep learning. On the left are statistical classical models. These are like our time-tested, interpretable models that no one likes to use these days. Everyone wants to just throw like a fancy machine learning or deep learning model at the problem. Statistical models have been around for decades, and they have a strong theoretical foundation. Machine learning models, think of them as, they obviously came after statistical, a little more advanced. These methods are data-driven and can capture complex patterns that perhaps your statistical models might miss. And finally, you have deep learning, which are like the newest player on the block. These are the heavy hitters. They take a while to fit. You can take it to its limit, and suddenly you have foundation-based forecasting models. The performance might be good, but then you have to judge based on the task at hand whether you want to go that route, whether you want to spend that kind of compute and time. I've tried to keep this, big picture. You can divide classical models into 4 bins. Again, or at least I have exponential smoothing family of models, structural models, autoregressive models, and then you can have like advanced or specialized models. And just so we know, we're spending a decent amount of time on forecasting in general and not just probabilistic forecasting, because the latter is really a function of the former. We need to understand the techniques, the tools for regular forecasting, and then expand into probabilistic forecasting. Exponential smoothing it's along with ARIMA-based models, they're the bread and butter of classical forecasting. Today, even with the onset of all these foundation-based time series models, they are still very, very competitive. The 3 musketeers of time series, error, trend, and seasonality. ETS models break down time series into all 3. TBATS is like ETS, but like just on steroids. You add in trigonometric competence, you add in complex seasonality. The one model that I'll highlight is ARIMA. ARIMA is just a seasonal alternative of it. We will use this in our notebook after we wrap up this presentation. Other than that, you're absolutely welcome to look into more detail about any of these models. Again, machine learning models. I mentioned these can adapt and learn from data in which perhaps traditional statistical methods are not able to. Tree-based models are the most popular, or at least among the most popular. You have random forests, gradient boosting models, which are XGBoost, LightGB, and CatBoost, very popular open source models, as simple as decision trees. Ensembling is where we combine different models.
Sorry guys, it seems Sankalp got the internet connectivity issue. Is suspect. Let me check with him.
All right. Yeah, sorry for the disruption, you guys. I'm not sure why the internet is acting up today. Yeah, I was just wrapping up machine learning based forecasting, and I think I was mentioning reduction, where the goal is to convert a time series with just, date time stamp and some value to a tabular form that you can input into your well-known scikit-learn machine learning models. And finally, deep learning. Really, you have RNNs, transformers, and LLMs. They're like the first generation, second generation, and third generation of forecasting models. I think most people might be familiar with like LSTM. GRU is the same concept, but with a slight modification. And then you have transformers, which became big a couple of years ago and actually are still used in industry to this day. LLMs are the bleeding edge. You have Chronos, Laglama, Morai. I think Nixla has one too. And in the notebook that we'll talk about, that we'll actually work with, I have a demonstration using Amazon's Chronos. So yeah, that should be exciting. We talked about, let's quickly recap. We talked about why forecasting is important, why probabilistic forecasting is important, different ways in which we can probabilistically forecast, and different tools we can use to get these forecasts. It's also important to evaluate these forecasts, right? Let's talk about the performance, how we measure the performance of these forecasts. As you can imagine, you have separate set of loss functions or metrics for point forecasts and separate for probabilistic forecasts. For point forecast, we are familiar with, say, bias, which tells us if we are consistently over predicting or under predicting. We have MAE and RMSE, mean absolute error, and root mean squared error, two very popular metrics. I won't really go into detail because I'm sure we're all familiar with them. Now for the probabilistic metrics. I have put in three popular ones. You have the pinball loss at the very top, which is used for quantile forecasts. It's like a game. This is a good way, I think, to explain it, where you can get penalized differently for over forecasting or under forecasting, depending on which quantile you're forecasting. And we'll see this in action in the notebook. CRPS, which stands for Continuous Ranked Probability Score, is a comprehensive measure, as you can see from the integral there. It's like grading your entire distribution of possible outcomes against what actually happened. And we'll also use that in the notebook. And finally, you have CRPS, pardon me, you have log S, which is the logarithmic score. It measures, just like the other two, how well your PDF, it matches reality. It is particularly harsh on forecasts that assign low probabilities to events that actually occur in reality. Just something big picture to remember with probabilistic forecasts is that we're not predicting a single number, but a range of outcomes with likelihoods. And these metrics that I mentioned just now, or loss functions, they help us gauge how well our entire PDF matches reality. Key attributes that we're essentially trying to capture through the metrics or loss function that I mentioned earlier, reliability or calibration. The TLDR, if you will, is about keeping our promises. If we say there's a 30% chance that the temperature will exceed 25 degrees Celsius tomorrow, then over many such forecasts, it should actually exceed 25 degrees Celsius about 30% of the time. It's kind of like being trustworthy. If I'm your friend and if I say I'll be late 1 out of 3 times, I better not be late all 3 times, right? Because that's how you lose trust. So that's what calibration or reliability really is about. Sharpness or precision, it's about being bold and specific in our predictions. A sharp forecast is like a sharp forecast isn't a wishy-washy forecast. Instead of saying the temperature tomorrow will be between 10 degrees Fahrenheit and 110 degrees Fahrenheit, I mean, of course it will be, which is safe, but it's not particularly useful. Instead, if I tell you it'll be between 70 and 75 Fahrenheit, and suddenly that's much more useful. So sharpness is all about narrowing down that range as much as possible while still maintaining reliability. And finally, skill or overall performance. It's about being better than the obvious. So like in weather forecasting, which is a nice example I often like to use, we compare our predictions to simple alternatives, like always predicting yesterday's temperature, known as persistence forecasting, or always predicting the long-term average for that particular season. If you're using a fancy forecasting model, you better at least beat those baselines. The tricky part is the balancing act. We want our forecasts to be reliable, to be sharp, and to be skillful all at the same time. But as you can imagine, it's easier said than done. There's often a trade-off between reliability and sharpness. We could make a super sharp forecast, like tomorrow's temperature will be exactly 75.62 Fahrenheit. That's so precise, but it's unlikely to be reliable. On the flip side, you could say it's between, like I said, 0 degrees Celsius and 100 degrees Celsius. Sure, but it's not very useful. Again, we're closing. We're coming to the close of this presentation, so I want to bring up a few pitfalls that I've seen when evaluating these probabilistic models. First is something I like to call oversimplifying accuracy metrics, and it's a trap that's easy to fall into, even if you're careful. When we work with probabilistic forecasts, we're dealing with a lot of information. Since our models don't just spit out one number, but like a whole PDF at times. It is more sophisticated, yes, but here's where things can go wrong. We try to boil down all that rich information into like a simple yes or no question. Let me give you a specific example. Imagine we have a weather model that's predicting tomorrow's high temperature. It's not saying tomorrow the high will be 75 Fahrenheit. Instead, it's saying there's a 60% chance that it'll be between 70 and 75, a 30% chance that it'll be between 75 and 80, and a 10% chance that it'll be between 80 and 85. Now, if you're not careful, we might be tempted to just check if the actual temperature falls between 70 and 75 and call it a day. If it does, we'll say the forecast was right. If it doesn't, we'll say it was wrong. But the problem with this approach is we are throwing away a lot of valuable information. If the actual temperature, it turns out to be 76, our simplistic evaluation, it would say that the forecast was wrong. But it wasn't technically wrong. The model did assign a pretty significant probability, 30%, to that bin, which is why it's always crucial to evaluate the entire PDF, not just a single, like, tiny range of it. We have tools for this, like CRPS that we covered, or logarithmic score, which we also briefly covered. These methods will look at how well the entire PDF matches what actually happened. Key takeaway, when we're dealing with probabilistic forecasts, we need to resist the urge to oversimplify. Another common mistake, it's something I call misapplying traditional error measures. We all have our favorite tools, but sometimes those tools just aren't right for the job at hand. Many of us are familiar with mean absolute error, root mean squared error, which is why we didn't go into a lot of detail about those. We've used these for years for point forecasts, and they've served us well. When we go into the field of probabilistic forecasts, these old friends, they can actually lead us astray. Let's say we're trying to predict next month's sales for a business. We have some fancy probabilistic model that says there's a 40% chance of $10,000 in sales, another 40% chance of $20,000 in sales, and a 20% chance of $30,000 in sales. We might be tempted to just average these out, which gives us an expected value of, you can do this, $18,000, and then use our trusty old MAE or RMSE metrics to see how close we got. Here's why that's a problem. We're taking this like beautiful detailed PDF and we are squishing it down into like one single number. We're losing a lot of high resolution information. And there's a more technical issue, I think it's worth mentioning, called Jensen's inequality. It's a pretty simple idea. Basically, it tells us that the expected value of a function of a random variable isn't always the same as the function of the expected value of that variable. In our case, what that means is if we take the average of our probabilistic forecast and apply our error measure, which is the wrong thing to do, we might get a different result than if we had applied the right error measure to each possible outcome and then average those. It is a subtle difference, but it can lead to like seriously biased results. So what should we do? Don't oversimplify. Don't use the wrong metrics. If you're dealing with probabilistic forecasting, use probabilistic metrics. And finally, we can at times overestimate model certainty. It's not uncommon, you've got a fancy probabilistic model and it's spitting out like these very precise looking probabilities. And it's tempting to say, well, if the model says it's 95% certain, so it must be right. But here's the thing, just because the model can give you a probability does not mean that that probability is actually spot on. Let's explain this through an example. Say we're in a hospital and we've got this cutting edge AI that's helping with diagnosis. It looks at a patient's data and it says there's a 95% chance this person has condition X. Now, if you're not careful, we might just go ahead and start treatment based on that high confidence. But if you really stop and think, is that the right move? And I don't think it is, because the 95% confidence, it might not be as solid as it looks. That's the model's confidence. It doesn't necessarily mean it is the reality's confidence, so to speak. Maybe the model was trained on a biased data set. Maybe it was trained on a limited data set. Maybe there are confounding factors that are simply not present in the input training data. The 95% output, it might be way off the mark. So what do we do here? We take a step back and we look at the big picture. One thing we can do, and that we often do, is we look at the model's track record. When it says it's 95% sure, how often is it actually right? And we have tools for this, such as the reliability diagram, which we'll cover in the notebook. They help us see if the model is overconfident or underconfident. What's the takeaway? Models, even fancy models, they are tools, they are not oracles, which is why it's important to combine what the model tells us with human expertise and any other evidence that we can get our hands on. Before we move on to the actual code, this presentation is just about to wrap up. I want to take a quick minute to talk about something crucial that when dealing with time series data in general, not just probabilistic forecasting, cross-validation. Here I've shown what k-fold cross-validation looks like, and this is something we're all familiar with. However, here's the thing with time series data, it has temporal order, duh. You can't just shuffle it around like you might with other types of data like we might be used to, like with k-fold cross-validation. Imagine if you're trying to like predict tomorrow's weather, but your model's been trained on data from next week. You suddenly have information leakage, you have bias, and it's not going to work, right? It's a big no-go in the forecasting world, which is exactly why you can't use regular k-fold validation. Well, at least not if you want believable results. So what do we do instead? We've got a whole toolkit of CV methods specifically designed for time series. I've listed here the more popular ones. We won't be going into significant detail, but please feel free to look into these at your own pace. Of course, this presentation will be shared, so you'll always have this in front of you. What I've demonstrated by a simple picture is walk-forward cross-validation, which is one of the more popular ones and which is something we'll be using in the library. Essentially, you start with a training set and you say a certain fraction of it is my actual training set and the rest is validation. And then you move that window forward and then forward and then forward. And so those are the folds of your data set. Again, for time purposes, we won't be going into detail about the other methods, but they are quite popular, so definitely feel free to take a look. And finally, as a prelude to our notebook, I have one slide about the ecosystem and specifically the library that we'll be using in the notebook. We're almost ready. This is the absolute last slide before we look into live examples. So full disclosure, I've borrowed this slide from the sk_time ecosystem of they have a bunch of presentations and notebooks. I think this slide does such a great job of illustrating what we're dealing with. What we are looking at is a unified framework for time series analysis and forecasting specifically. At the bottom, it says sk_time. Think of that as foundation. It's this open source library. It's really just actively developed that brings together a whole bunch of time series tools under one roof. It's not about just forecasting, as you can see from the very bottom row. It covers classification, regression, all sorts of transformations. It's like the Swiss Army knife of time series libraries. My favorite part, and the reason I like using it so much, is because of the green boxes. Those are other popular time series libraries, completely different developers, different specific tasks. And what sk_time does is it says we're not going to reinvent the wheel. We'll give you adapters to these different models. And if some particular library has a breaking change, then sk_time issues a pull request to try and fix their own adapters. So it saves you a lot of time. It gives you one API, so you don't have to start learning the APIs of different libraries, which is extremely helpful. Okay, that was the final one. And now we're gonna move to the notebook, and I would very much like to get through that. Okay, let me stop sharing here. Okay, I'm just gonna pull up the notebook and reshare. Bear with me, almost. It's on VS Code.
No worries, no worries.
All right, there it is. I'm gonna go ahead and minimize. I think Hirsch, you said I quickly looked over the chat. I think you shared this, right? Yeah.
Yeah.
Yeah, appreciate that. Thank you. Okay. All right, here we go. Let me just move this around so it's not in the way. Okay. we'll start with, again, it's a Jupyter notebook. You are absolutely welcome to, run the cells alongside me. Always like to suppress some warnings. And then I already have in my environment these packages installed, but I'm going to wait maybe a minute or so in case you guys don't. There we go. I'm just getting these messages that all my requirements are satisfied, which makes sense. But I'm just going to wait a second. And if there's some problem with installation, let me know. All right, maybe like 10 more seconds and I'll move on. Oh, just so people focus on the notebook. Hold on, let me just, and I think my bandwidth is also limited, so I'm going to stop the video. But as long as you're able to see the notebook, that's all that matters. Herj, did anything pop up, major issues with installation, or can I just move on?
Yeah, we can.
All right, perfect. Okay. Essentially, what we'll be doing here is trying to see with actual code the various concepts he talked about, the classical model, the machine learning models, deep learning models, how to evaluate them, how to improve the probabilistic forecast, the different types of probabilistic forecasts, and just get a hands-on demonstration. I just want to make sure. You know what? I think I might have forgotten TS Bootstrap. So if you want to do pip install TS Bootstrap. Yep, yeah, sorry about that. There we go. I like to have a black background for plotting with like large text and large fonts and whatnot. So I'm just gonna go ahead and run this at the very beginning. We begin with data exploration and data preparation, really. I'm going to use the simplest data set, one of the simplest data sets in time series, really, called the airlines data set. This is on purpose. So our focus is not so much on analyzing the complexities of the data set, but we can focus more on the probabilistic forecasting part. So I went ahead and ran that cell. This is the monthly airline passenger set from 1949 to 1960. It's a relatively simple data set. As you can see, there is a trend, there is a periodicity, and of course, the actual cyclical values, they increase in time. That is a qualitative way of saying all this. How do we quantify that? Usually, when doing EDA, we break down these things into trend, seasonality, and noise. So, quick digression to talk about stationarity. Stationary time series, which, again, note that this is not a stationary series, or more specifically a weekly stationary series, is one where the mean and the variance are constant over time. And why is a stationary time series a big deal? Because several models either require the inputs to be stationary or they perform better with stationary time series. As you can see, this model or this time series isn't stationary, so we're going to go ahead and stationarize it. One simple trick is to just do like one step differencing, which is exactly what we do here. And then we just go ahead and plot it. There we go. Much better. This still isn't completely stationary, and there are more advanced ways of making data sets stationary, but its mean is already stabilized. And for our purposes, for this exposition, it should be good enough. Another concept with forecasting in general is ACF and PACF, so autocorrelation function and partial autocorrelation function. Without spending too much time on these, because again, this will take time away from our probabilistic discussions. What do they help us do? They help us identify patterns, which will help guide model selection. And they are very crucial for traditional time series models, such as ARIMA. I think I mentioned earlier, ETS and ARIMA based models are like the workhorses of time series forecasting. They've been around forever, and they still give you fantastic results several times. So we import PSCF and ACF from the stats models library, and we just go ahead and plot. There we go. What this is saying is kind of what we expected. We know that our monthly airline data set has a seasonality of 12 units, so 12 months, which makes sense because, airline passengers, as you can kind of intuit, have an annual seasonality. It's unlikely that number of passengers this June will be significantly different than the one last June or the June before that. So what we're getting here is a spike outside of the confidence intervals at 12. If you look at the lag on the x-axis, and then multiples of 12. This is the ACF plot, and this is the PACF plot. Again, you get a spike at 12 and not the others, which is exactly what you would expect from PACF. PACF is it's partial, which means it looks at a lag just by itself and not in combination with other lags, which is great, which basically verifies something we knew already, that our data set has a seasonality of 12. Fantastic, now we can quantify it. Okay, that was a quick EDA, leading us to our next section, making and evaluating probabilistic forecasts. Before we do any kind of forecasting, any data analysis, first thing to do is to split the data into a training set and a test set. Believe it or not, I've seen models in production where people do all kinds of feature engineering on their time series data and only then split into train and test, which results in a lot of leakage and your forecast being overly optimistic. So immediately, the first thing you do is you split your data set and you just work with the training data. So this is the training data from 49 to 58. And the test data is, again, from 59 to 60, so just 2 years, which means it has 24 data points, just FYI. I mentioned at the beginning of this notebook, we'll be working with classical machine learning and deep learning models, so one of each type. For classical, I've chosen ARIMA, which is a workhorse of TS forecasting, specifically SARIMA, where the S stands for seasonal. ARIMA models have 3 variables of interest, P, D, and Q. P is the AR, or autoregressive part. This is an integer which denotes how many past values we should use to predict future values. I is the integrated or difference part, which means it says how much to difference the time series to make it stationary. And Q is the moving average, which means how many past forecast errors do we use to improve future forecasting. For SARIMA, it's just you have capital P, capital T, and capital Q. It's just a seasonal analog. In fact, we won't be setting these parameters by hand. We will be using auto ARIMA, which, as the name implies, uses certain heuristics. In this case, we're using the Bayesian information score to find out what these parameters should be. So we begin by predefining a dictionary of all the various parameters that will go into auto ARIMA. As you can see, we don't actually tell what the P, D, and Q should be. We give it ranges. We set SP, which is a seasonal component, to 12 by hand. We start by, and when I said auto ARIMA, there are 2 major auto ARIMA implementations. One is in PMD ARIMA, which is a different library, and another is in Stats Forecast, which is a library by Nixla. The latter is significantly faster and more actively maintained. That's the right here. That's the from stats forecast. That's the one we're using, but not directly from the library, but using the adapter that's been implemented in sk_time. We import some other transformation modules, specifically 𝗣𝗦𝗕𝗓𝗓 and 𝗣𝗥𝗢𝗕𝗓𝗓𝗓 and differencer. I'll show you why. Okay, so I'm calling this a pipeline because what I'm doing is I'm moving from left to right. First, I'm differencing my time series, and by default, this has a lag of 1. Then I deseasonalize it by giving it a seasonal period of 12. Then I detrend it. And finally, we pass the parameters that we define to stats forecast AutoArima. I probably didn't need to do these things because AutoArima automatically finds what the small d is, what the seasonality is. But it doesn't hurt. Empirically, what I found is if you kind of pre-process it before giving it to your models, your auto models, it helps with their forecasting a little bit, and it definitely helps with reducing the compute time because now they're looking for those parameters in a constrained space. We go ahead and fit it to our data. I like this little visualization. So you have your differencer to deseasonalizer to detrender to actually model. The model is done fitting, so go for it. There we go. We run it. Then we go ahead and actually look at the best fitted parameters. That's what this whole cell is all about. Okay, so what are these parameters that it identified? P1, D0, Q1. Remember, D was a differencing term, and it says that the series does not need to be differenced, which makes sense because we've already sort of pre-differenced it. So the model is saying, we don't need to difference it anymore to make it stationary. I'm happy with the series as I received it. Then we go ahead and use the .predict method from this fitted pipeline from sk_time. Again, go ahead and run it. .predict will give you point forecasts. Plotting always helps, so go ahead and plot these. Training data overplotted with forecasts. Something interesting to note that we are under forecasting, and you can of course work on that by tuning your base model, trying different transformations, etc. But that's not the focus of this presentation of this notebook. This concludes point forecasting with the classical model that we've been talking about. Let's move on to probabilistic forecasting. In sk_time, for the purposes of this particular discussion, we have interval forecasting, quantile forecasting, variance forecasting, and distribution forecasting. We'll avoid variance forecasting for now. Key differences, we've already covered this, so I won't spend a lot of time on this. Interval forecasting gives you a simple range. Quantiles gives you, it's like higher resolution. It gives you specific probability points. And distribution forecasting, it gives you the complete probability picture. The specific methods we'll be using are .predict interval for interval predictions. It takes as input the forecasting horizon and coverage. Remember when we saw the slide deck, there was an alpha parameter with interval forecasting. So that's essentially what this is. Let's go ahead and actually do it. I like running code. Let's see what did this here. This was our fitted pipeline. We called .predict interval with a 95% coverage. And just for sake of pretty plotting, if you will, I concatenated that with the test set. So this is the lower and upper bounds of the 95% prediction interval. And these are the actual ground truth values, which of course the model didn't have access to during training. And this is just for comparison purposes. This is great. And let's go ahead and plot this exact thing. You can also use the dot plot or the plot series utility or plotting utility from sk_time by passing it what the prediction interval should be. This is what it looks like, the same point forecast that we saw earlier. A couple of interesting observations. The interval width increases as you go from left to right, which makes a lot of sense because we've trained on the training set and we're doing like almost one-shot forecasting on the test set for all 2 years. The further you are from the training set, the worse your forecast will be, which makes sense, which is the large interval. And another observation is a lot of these forecasts go below 0, which is fair because at no point did we tell the model that, hey, these represents number of people, our y-axis, passengers, which obviously are 1 or greater. So the model has absolutely no idea what this means. Of course, it will forecast something smaller than 0 if that's what naturally happens. There are ways to sort of curtail this behavior by appropriate transformation of the input data, or you can just post hoc clip the values at 0. That's another approach, just something to be aware of. Quantile forecasting is done by the dot predict quantiles method. You have your same forecasting horizon. And I've mentioned a few times quantile forecasting is interval forecasting, but at a higher resolution. So it takes a whole list of quantile points. You can pass in 0.01, 0.02, 0.99. So that's the quantile at which you want the forecast. If you pass in multiple, it will give you multiple forecasts simultaneously. Let's go here. Let's go ahead and run this. Here I asked for forecasts at 3 different quantiles, the 2.5 percentile, 50th percentile, which is by definition the median, and the 97.5th percentile. Again, just a quick mental calculation, 97.5 minus 2.5 is 95. So if you subtract this value from this value, that's the interval, the 95% interval. Pretty plotted along with the true number of passengers. And let's go ahead and plot this just like we did earlier. There it is. Green is the median. This is the lower quantile, and this is the upper quantile. So as you can see, the forecasts are good in the sense that their coverage it's good, but their interval sharpness, which is a metric that we discussed in the presentation, is not very good. It gets very wide. It's like saying, okay, the number of passengers are between -100 and +1,000. Sure, but I'm sure we can do better. Finally, for distribution forecasting, we use the .predict proba method. This uses the skpro library. So you call you just have to install the library, and sk_time takes care of it in the back end. What you do is you just exactly like we've been doing so far. This is the fitted model, and you call .predict proba on it. And you get this by definition, it does normal model, and then you get this fitted object on which you can then call the .quantile method to again get those quantiles. So same thing as before, the lower, middle, and upper quantiles with the number of passengers. A quick note on the consistency of methods. It is not guaranteed by sk_time that the various values that these methods will output will be consistent or equal to one another. It is a weak interface requirement, but it is not enforced. So the best thing to do is figure out which one you need for your use case, and then just use that specific method. Quick evaluation. We've already covered this in the presentation. We'll start with very quickly 2 important metrics for point forecasting, and then we'll move on and spend some time on probabilistic forecasting and see what the actual code to generate those metrics look like. For point forecasting, we already used root mean. We talked about RMSE or root mean squared error and MAPE. MSPE is literally just the percentage equivalent of RMSE. You can call them directly from scikit-time or skTime, define the object and pass in the true values, and the 𝗣𝗦𝗔𝗕𝗓 was, remember, the point forecast and not probabilistic forecasts. There we go. It tells you that we have 14.8% MAPE and 2.4% MSPE. Are these values good, bad? We really don't know. Oftentimes when companies start using probabilistic forecasting, they ask you, hey, what should be a good value, right, for these metrics? There is no universal answer. Of course, the lower the better, but a good answer to this question more often than not is, what does the business require? What is the threshold? Even if it's a science experiment, what is good enough? If we are below that good enough threshold, then we're all good. But that's more of a business decision than a forecasting decision. Okay, let's go to evaluating probabilistic forecasts. We've already covered several of these, but what we'll do in this notebook is actually plot these out. We've used the term coverage several times, or calibration, right? It measures how often the true value falls within a predicted interval. So this is dummy code that I have here. I have a dummy 𝗣𝗦𝗔𝗕𝗓, where I just generate a sine curve and add noise, and 𝗣𝗦𝗔𝗕𝗓, where I say, okay, I'm unable to capture the noise. I've simulated good coverage and poor coverage, and we just go ahead and plot. Let's look at the images. So what I'm saying is the top one is good coverage, or has good coverage, and the bottom subplot has poor coverage. Why? Coverage, remember, is the percentage of times in which your interval actually encompasses the ground truth. If you look at the lower plot, a lot of those true values right here, they lie outside the interval that we've overplotted, whereas that is not the case in the top subplot. Hence, I'm saying the top subplot has good coverage and the bottom has poor, and we should endeavor for our forecast to have good coverage. Why is it important? We've already covered this. It indicates the reliability of interval forecasts. It lets the stakeholders know whether or not they can use your probabilistic forecasts for downstream decision making. Sharpness, we've talked about this earlier in the presentation. We talked about this just above when talking about interval forecasting. Same thing. We use the original synthetic 𝗣𝗦𝗔𝗕𝗓, dummy lower and upper bounds for good sharpness and bad sharpness. The top subplot has sharp intervals, which is what we want, and the lower has wide intervals. This should be pretty self-explanatory. Why are sharper forecasts desired? Well, they're more informative, provided they are well calibrated. Something that we've highlighted is we need to balance between sharpness and coverage, and CRPS actually is able to do this. The CRPS metric that we covered in the presentation, and that we'll look at just later in this notebook. Calibration. What is calibration? It's same thing as coverage, but it applies to the entire probabilistic forecast. So if we predict a 70% chance of rain 100 times, it should rain about 70 times. And there is a very nice curve or a figure to visualize how well calibrated your forecasts are. It's called the calibration curve, and you can just import it from sklearn. We generate synthetic data and then synthetic outcomes. I'm not focusing a whole lot on the code because you'll have access to the notebooks and you're welcome to play with the code yourself. What I want to do is focus on explaining the concepts with these visual tools. On the y-axis, we have the true probability. On the x-axis, we have predicted probability. We covered in the presentation earlier that just because your model tells you it's 95% certain about something doesn't mean that it necessarily jives with reality. It's something you need to check for. This is that check, if you will. Ideally, as you can imagine, we want to be on the one-to-one line. How do we interpret this particular plot? Well, if you look at, say, 0.7, right? This point right here. When the model is forecasting that probability of the event happening is 0.7, the actual probability is like 0.5, which means your model is overconfident. So essentially what is happening is up until 50%, the model forecasts jive very well with reality. And after that, it just starts becoming very overconfident. And we won't really know that until we look at a higher resolution image like this. As you can imagine, it's important for overall forecast reliability. Another important tool in our tool set for evaluation is the PIT diagram. There we go. It's another visual tool. It shows the distribution of observed values within predicted distributions. Let's just jump to it. Why don't we? Just note that I've shown you, I'm going to show you what a perfect pit diagram should look like, what is an under-dispersed pit diagram, and what is an over-dispersed pit diagram. Okay, so perfect is the red one, which across all the probabilities will stay at 1 density, and pardon me, and under dispersed, which is the blue one, has this sort of a dome feature, and over dispersed has the U curve, where it has low density at middle points and very high density at lower and higher probabilities. Let's interpret this, because this is not just something nice to have, it's actually very critical in evaluating our probabilistic forecasts. We mentioned, perfect forecast is the red line or the red curve. U shape is the under dispersed forecast, which means it's too narrow. Inverse U shape or the dome shape, it's too wide, which means if you have a skew like that, which it indicates systematic over or under dispersion. It helps reveal biases and miscalibration in your modeling forecast. It tells you that it complements the above reliability diagram or calibration diagram that we saw. It tells you that if the true probability is, let's say, closer to 1, I'll do okay. If the true probability is closer to 0, I'll do okay. But for the middle probabilities, I'm just looking at the gray curve here, middle probabilities, I'll be very low. I'll be very uncertain. I'll give you the wrong answer. And our goal when we fix these forecasts is to bring them in line with the red curve, with the uniform distribution. Another one, resolution, we didn't cover in the presentation, but it's also an important one. It measures how much forecasts vary across different situations. Let's look at the figure, and I'll explain it just using the figure. Okay. On the right, I have a low resolution forecast. On the left, I have a high resolution forecast. Essentially, what we're saying is a low resolution forecast is just going to forecast the same value for a whole different range of scenarios. It's always going to say the probability of something happening is 50%. The probability of something happening is 40%. And this output doesn't change as a function of the underlying true value. Whereas we know just in reality, in real life, how certain or how uncertain you are about something depends on what that something is, which means in reality, you will kind of expect different probabilistic outcomes from your model. And that's a high resolution forecast. Pinball loss, we talked about it, we saw the equation, but here we'll try to get sort of an intuitive grasp on it. It's a very simple loss. This is the formula for it. It goes from 0 to infinity. Lower values indicate better calibrated intervals. again, let's look at the plot because I immediately like to look at this is what the plot looks like. So on the x-axis is the difference between the predicted value and the true value. On the y-axis is pinball loss. Immediately, you'll see that it's an asymmetric loss function, which means if you over forecast something, it doesn't penalize you as much as it penalizes you if you under forecast something. So that's exactly what's written here. Left side has a steeper slope and represents underestimation, whereas right side has a gentler slope and represents overestimation. Why this asymmetry by design? Imagine planning a road trip. Running out of gas, which is underestimating, is worse than having too much gas, which is overestimating. These are the kinds of scenarios that pinball loss function is designed to capture, is designed to attack. We talked about CRPS, and let's look at the equations and what the plot looks like. Same thing, it varies from 0 to infinity. The lower, the better. It captures both sharpness and calibration simultaneously. So it's honestly my most often used loss function. It requires as an input the entire distribution. Remember, we talked about 4 types of probabilistic forecasts. CRPS requires access to the third type, the distribution. You can, of course, approximate it if you have a number of quantiles, because you can think of a whole PDF as essentially an infinite number of quantiles. So if you have a large number of quantiles, you can go ahead and approximate CRPS. We'll go ahead and plot this. Let's look at the figure. In this particular figure, 1 on the x-axis, the value 1 is the true value. And what we've plotted are 2 CDFs, the original CDF and the forecasted CDF. The original cumulative distribution function will, of course, be 0 right up until it hits 1, and then it'll suddenly become 1. That goes without saying. In this dummy example, forecasted CDF, it's not too bad. The idea is to bring the blue curve in line with the yellow curve, is to reduce the total area under this curve. Just a quick clarification, CRPS is not the area under the curve, but it's proportional to the area under the curve. CRPS is the probabilistic equivalent of the mean absolute loss. But for visualization purposes, you can think that CRPS is about reducing the area under this curve. Like I mentioned, blue line it shows the probability of forecasted values and has a smooth S shape. The key focus is the area between the blue and orange lines, which is what we want to reduce. And we've already covered this part. Why it matters, it considers the entire PDF, and it rewards both sharp and well-calibrated forecasts, which is exactly what we want. So, just a quick recap. We started this notebook by talking about the data set that we'll be using. Then we moved on to evaluating deterministic forecast. Then we talked about evaluating probabilistic forecast. We took an ARIMA model, specifically an auto ARIMA model, and generated both probabilistic forecasts and deterministic forecasts. Now we'll actually calibrate pinball loss and the various curves that we've been talking about for these kinds of probabilistic forecasts. Same thing, we're going with the interval forecast that we generated from our ARIMA model. Remember, pinball loss function is very much dependent on the quantile or the coverage. So we want, since we generated both a lower quantile, the 2.5th percentile, and an upper percentile, we'll calculate 2 separate pinball losses, and then we'll just average them. So when you go ahead and run this, you get a lower pinball loss, which is good, an upper pinball loss, which is worse, which tells you that you're doing better on when you forecast like lower quantile values than you're doing when you forecast upper quantile values. and that's the average. This is like, these are the numbers that we'll try to improve as we move into machine learning models and deep learning models. Same thing, pardon me. I think this might perhaps be a mistaken copy. There we go. We calculate CRPS. Remember, for CRPS, I mentioned we need the entire distribution object. So we use 𝗣𝗦𝗢𝗕_dist, where we use .predictProba method from skTime. We pass in the entire object and output a value. This value might by itself doesn't tell us as much as it would if we compared it to CRPS values from different models. It's relative and it's dependent very much on the problem at hand. But I wanted to demonstrate how you would calculate the CRPS value. Let's go ahead. We talked about calibration diagram. We talked about pit diagram. Let's see what they actually look like with our forecast from our ARIMA model for the airlines passengers data set. So our calibration curve is absolutely off. We are not doing very hot. Key observations. Some 2.5% quantile predictions are negative, which doesn't really make sense for passenger counts. This is something we covered already. Why does the curve look unusual? We have negative lower quantiles. We have wide intervals, which really skew our pit calculation. Model might be underestimating passenger counts, and your increasing uncertainty is not reflected in this calibration curve. So what we need to do is bring this curve, either play with data transformation, play with the modeling approach, or combination thereof, to bring this blue curve in line with the red curve. Right now, what this tells us that our forecasting is really bad. Same thing with the pit histogram. Remember, we talked about how this should ideally be a uniform distribution. Just at the one line, but it's not doing so well. And we already knew this from the calibration diagram. It's skewed very much towards the 0.55 area with a huge density peak at about 0.6. It is far from a uniform distribution. It is overrepresented in this area and underrepresented at higher probabilities. Recommendations, we've already covered this. Let's prevent negative predictions by using a log transform. Investigate if we can use other types of data transformations or modeling approaches to curtail the wide intervals. And if this was in a production setting, you would even consider using this in conjunction or as an ensemble member in like a large stacked model, or combining some sort of by using weighted voting method to combine predictions from multiple different models. TLDR, models probabilistic forecast needs serious calibration work. That is something we'll try a little bit in this section. We're focusing on two things, tuning and reduction. Pipelines is something we've already covered. Remember, when we created our pipeline, the ARIMA pipeline, we used a differencer followed by a deseasonalizer, followed by a detrender, followed by the actual model. That's a pipeline. It takes care of the transformation and then the detransformation of the model for us, so we don't have to think about that. The two remaining problems that we'll cover are tuning, also known as HPO, hyperparameter optimization, and reduction. I briefly mentioned this earlier, where we convert a time series into a tabular form suitable for inputting it into a regression model. Let's talk about tuning. When we do HPO, it becomes critical to define some sort of cross-validation schema, which is the reason, if you recall, in the slide deck, we touched on cross-validation methods. 𝗣𝗥𝗢𝗕𝗓 has access to grid search CV, random search CV, 𝗣𝗢𝗓 search CV. As you can imagine, it uses 𝗣𝗢𝗓 instead of simple grid or random search. This is just pure data science work, but applied to time series. You define a metric that you want to maximize or a loss function that you want to minimize. We talked about simple train test split. That's what we've been doing so far. The second we talk about cross-validation, there's the expanding window and the moving window. These are the pros and cons for each. A little description, please feel free to read at your own pace. We've already covered this, which is why I'm kind of moving on. This is a simple train test split. This is what we've been doing so far. We train on this train model, and then we forecast on the test. However, when doing cross-validation, you need to have multiple such splits. So you have your training model. This is fold 1, fold 2, expanding window expands, fold 3, expanding window even expands further. A better name for the test set here would actually be the validation set, since you're training and validating, training and validating, training and validating, and the test set actually remains fixed. Moving window, similar. I like visualizing things, so I'm gonna use the sliding window splitter from 𝗣𝗥𝗢𝗕𝗓 to show what this looks like with our data set. So we would have 24 folds. In the first fold, this would be our training data, and we'll forecast next point. Training data, forecast next point. The blue part is the training data, and the rest is the forecasting, it's the validation set. It's a sliding window, moving window, as opposed to expanding window. So the total size, the number of points inside the training window remain constant, as you can see in the parallelogram. With that little digression out of the way, we'll actually now start doing HPO on our ARIMA model and see if that actually helps improve results. We've already specified the data forecasting horizon is essentially the length of DF test. We create a pipeline slightly differently now, and this is just so after we are done finding the best parameters, we can put it back in again and create the best pipeline, if you will. So what are the parameters which we'll be optimizing is lags. By default, the differencer had a lag of 1. I say, you know what, let it be, maybe a lag of 2 is better, maybe a lag of 3 is better. Let grid search CV find that. Seasonality, I put in a seasonality of 12. Was like, okay, I'm just gonna let that be a free parameter as well. And the model type, it can be additive or multiplicative by definition, or by default it was additive. But since we're doing HPO for the sake of exposition, I've let that be a parameter in the grid also. As you can see here, I give 2 seasons, I give 3 differences, and 2 types of model parameter. When you run this, here, actually, I don't want to run this because it takes a few seconds, but essentially what you get, feel free to run this locally. It says the best seasonality is 24, so 2 years, not 1 year. The best lag is still 1, and the detrending model is best is actually not additive, it's multiplicative. Now, mind you, this might not necessarily be the best HPO parameters, because they're a function of the time for which you let your hyperparameter optimization algorithm run. It's possible if I had given it a larger amount of time to run, it might have given me a different set of parameters. But we'll see later that with these improved parameters, we actually get an improved model. So let's see if this improved results. Yeah, so after I got these models, I recreated a pipeline and I called it final pipe ARIMA. Pardon me. We go ahead and repeat the exact same process. The calibration diagram looks slightly better. It might be difficult to visually compare. Same thing with the PIT. It was very much peaked close to 0.55, 0.6, but now it's shifted a little bit to the right and spread out a little. So it is still not ideal, but it's better, or in other words, it's less sucky than before. And we can actually quantify this with a pinball loss. So Originally, our pinball loss was 13.28 was the average. On the low side, it was 8. On the high side, it was 18. And we do the exact same calculation with our ARIMA model, which has been tuned using HPO, and we get different results. We slightly improve. We get worse on the lower side, we get better on the high side, and from 13.28, pardon me, from 13.28, we drop to 13.26, which is not, I will admit, it's not a great improvement, but it highlights two things. One, that HPO did give us an improvement, and two, it highlights the importance of actually using these probabilistic tools to capture the quality of your probabilistic outputs. One of the pitfalls I mentioned in the presentation was people try to condense this information and use deterministic or point forecast metrics. And this actually tells you that if you actually use the right metrics for the right job, you will be able to capture how good or how poorly you are forecasting, in which case it's the latter, which is totally fine. Okay, quick recap. We have used AutoArima to do point forecasting. We've used AutoArima to do probabilistic forecasting. We've tuned AutoArima using the SK time tuning modules, and it's improved result very slightly, but it has improved result, which tells us that HPO works. Next, we'll do the exact same thing, but this time with machine learning models. Oh, quickly before that, with AutoArima natively supports a dot predict interval method, a dot predict quantile method. What if you have a favorite forecasting model, which is not conducive to probabilistic forecasting? In this case, I've shown that if you import exponential smoothing from SK time and you check whether or not it has a capability for probabilistic prediction, it does not. But what if you're like, hey, my company has been using exponential smoothing for a while, and our deterministic or point forecasts have been fantastic. I would love it if I can keep using this same model to get probabilistic forecasting. You can do it very easily with SK time. There are a few ways to do it. The way I've chosen to do it is by using this library that I created called TS Bootstrap, which does time series bootstrapping. In brief, what it is you take your black box forecasting model, you take your original time series data, you use my library to create these copies of your time series data, feed it into your point forecaster, and get as many point outputs as you created copies of your time series data. All of this wrapping has been made very easy by the adapters available in SK time. So you use the TS Bootstrap adapter, and these are the specific type of bootstrapping, time series bootstrapping algorithms that we've used. I won't go into detail because it's a whole different presentation, but just know that this adapter lets you do time series bootstrapping. So we deseasonalize, we detrend, and then we use something called bagging forecaster from SK time, which allows us to do this. My forecaster here was my forecaster was the exponential smoothing model, which was completely deterministic. You put it inside bagging forecaster, put it in the pipeline, and suddenly you check again if it supports interval forecasting, and voila, it does. Now it can be used just like we've been using our ARIMA model. It gives you interval forecasting. It gives you a lower value and upper value. If you wanted, you could have called predict quantile instead of predict interval, and so on. I've specifically used TS Bootstrap adapter, but SK time has other ways of converting a point forecaster into a probabilistic forecaster, and I've put them here for your reference. Definitely check these out. Okay, I promised you will use a machine learning model for probabilistic forecasting, and I'll show you how. The name of the game is to create features in the way we are familiar with regular machine learning forecasting or machine learning regression from our time series. A simple way to create features is to use lags. And for this, we just use the window summarizer from SK time. I've called this transformation fit predict or fit transform. I wanted to show you what it looks like. And I've essentially what it does is recall that our data actually started at from 1949. But we've dropped the first 3 years of data because here I said I want my lags to be 36. So the first time period has 36 lags. It has the actual value at that time plus 36 lags going back. This is X train just for exposition. You separate X train and Y train. You take the 0th lag value that I just showed as Y train. Now we've just generated lag features. Now we're gonna generate date time features, which is demonstrated in this cell right here. You call the date time features transformer from sk_time, and you'll create features about year, quarter of year, month of quarter, based on the date time stamp. What does this look like? Okay, so if it's the 1st of January in 1952, that's in the first quarter of the year. January is the first month, and it's also the first month of the quarter. Let's look at January, February, March, April, May. May is the 5th month of the year, which is why month of year is 5, but it's the 2nd month of the quarter. So it's 1, 2, 3. Yeah, it's the 2nd month of the quarter. And hence those two numbers are different. We can generate even fancier features using a library designed especially for generating features from time series data called tsfresh. As before, sk_time has, you've already installed this in the very top cell of this notebook, and sk_time has an adapter to tsfresh. tsfresh can actually generate about 770 features from a univariate time series, which will get computationally expensive. So here I've chosen to just generate 10 basic features by putting in minimal here. This is just some code that helps you generate features. Please feel free to run this locally. What I want to show is what are the features that are actually generated. So remember, we had generated lag features, and then for each row, I gave it as an input to tsfresh. And it said for the first row, where you had 36 lags, which means going back 3 years, the sum of the passenger values, the median, the min, or the mean, the length column is the same because it's all 36, standard deviation, variance. It calculates all of these automatically without me having to specify. We can actually print out what are the different columns here. So it has 10, median, mean, absolute maximum, minimum, and you can check out the documentation in both sk_time, which links to the tsfresh documentation for detailed description about these features. Then this was just for demonstration purposes. This is not how I would use it to actually fit the model in sk_time. sk_time is all about using pipelines. You don't want to do anything by hand. So the machine learning model that I'm going to be using is k-neighbors time series regressor. It's like k-nearest neighbors, but for time series. I use the tsfresh extractor. I use the datetime features transformer. And note that I'm not fitting any of these separately to my training data and like creating features or creating data frames by hand. These all go into a pipeline right here, make reduction. And I just call the whole thing, I call the .fit method on the whole thing. It's a one-liner. It takes care of everything within the pipeline. And then we go ahead and print out just like before, we print out quantiles, lower, median, and upper with our k-nearest neighbors regressor. So these are the values. Let's go ahead and see qualitatively, and then quantitatively, if we've improved, we'll go ahead and plot the exact same thing. In fact, what we see is calibration diagram in some parts. In the lower part, it's better, but here it's worse. So the calibration curve that we get is clearly a strong function of the model and the transformations we choose. Same thing for the pit histogram. It's gotten so much better in the earlier parts. It's gone under the y=1 density level, which is what we wanted, but it's doing really poorly at high probabilities. Let's get quantitative metrics. We calculate pinball loss. On the lower side, earlier we were getting 6. Now we're getting 3, which is fantastic. The lower, the better. And this can also be seen from the pit diagram. We're getting more uniform distribution for low probabilities, but we're doing significantly worse at higher probabilities. And the average went from 16 to 21. So overall, the way this pipeline is designed is giving us overall worse performance. It's giving us definitely worse performance on the upper ends of our probability distribution. And we know this information from the pit diagram and the calibration diagram. Second step here, of course, would be to fine-tune this and see if that, and fine-tuning could actually, you can expand that concept to the AutoML concept. You can say, I'll give you a list of 5 machine learning models with a fixed set of transformations for the time series, figure out which model is the worst part or which model is the best based on the metric that I want to optimize, either CRPS or pinball loss. That's being left as an exercise, except just to save time. And you can copy and paste code from above with just change variable names, and you should be able to get results very easily. Finally, if you give a presentation in August of 24, you can't really not talk about LLMs. Everyone and their mother is using them. This is where we use the third family of models. We started with statistical, then machine learning, and now we're going to use a deep learning model, a foundation model, specifically Chronos from Amazon. Chronos publicly has 5 different versions available. As you can imagine, from tiny to large, it's get larger and more expensive to train. We'll use mini. I found trial and experiment for it. It gives you good results, and it gives you results quickly. You can use, for device, you can use CPU or GPU. I've decided to use CPU because I'm running on this on my laptop, which doesn't have an NVIDIA GPU. And I imagine this could be the case for several of you. We go ahead and we import this from Amazon. Something that the dot from pre-trained part is really important here, because what this tells us is we aren't actually going to be training this on our training set. It's a one-shot, or it's a zero-shot forecaster. This model has been pre-trained already. We're just basically fine-tuning it on the training set. It's been trained on like a large repositories of time series of varying properties. We will be fine-tuning it on our data set and then forecasting it one shot on our test set. When we go ahead and forecast, we save everything in Chronos forecast, and then we start visualizing. Again, I get 3 quantiles. Lower the test data is the ground truth is the yellow one. Our upper bound is the red line, and the lower bound is the blue line, and everything in between. I concatenated everything for pretty plotting here. Same thing we've been doing before. We'll get the pit diagram and the calibration diagram. There we go. Okay, looks different. It's hard to say if we've improved overall or if we've not. Pit diagram. Pit diagram actually looks better because we are significantly closer to the one value that we want, and we're not as peaky. Earlier, we were very peaky on the right side. The y-axis had very high values, and now it's getting better. This was the qualitative part. Quantitative part, get the pinball loss on the lower quantile, higher quantile on average. You see, on average, with our ARIMA model and our fine-tuned ARIMA model, we were at 16.3. With our machine learning model, we did worse. And with Chronos, we're actually doing the best so far. And this was by using the Chronos mini version. For comparison, this was untuned ML. Like I mentioned, we were actually doing worse. So this wraps up our presentation. I left one part as exercise for you. Go ahead and just tune the machine learning model yourself. And yeah, I hope it was helpful.
Thank you very much, Sankalp, for the very interesting presentation. It's really interesting. So we got few questions. I sum up them into one chat, and I just put it onto the chat. If you could answer those.
Absolutely. Let me share my screen again. Oh, pardon me. Let me turn on the video again. Thank you. Okay, I'm going over them right now. The 4 questions, yes.
Yeah.
Pardon me. Oh, yeah, the confidence versus prediction interval. That's a really good one. Confidence interval, it provides a range of plausible values for a population parameter based on sample data. It's used to quantify uncertainty around some estimate of the population parameter. Like, how confident are you that the mean is actually what you say it is? How confident are you that the median is actually what it is? For example, we are 95% confident that the true population mean falls between X and Y. Whereas a prediction interval, its purpose is to account for both the uncertainty in estimating it's like a superset. So both the uncertainty in estimating the population parameters, as well as the inherent variability in individual observations. We predict with 95%, we predict that 95% of future observations will fall between A and B. And notice how I talked about future observations. So what we've been doing so far is really working with prediction intervals. Hopefully that helps. So the TLDR would be the scope. Confidence interval has a specific narrow scope. Prediction interval has a wider scope. Is quantile forecasting at alpha level the same as the upper bound of a prediction interval with 2 alpha? Oh, let's see. Quantile forecasting is the upper bound of a prediction interval. If I get a prediction interval with 2 alpha, let's say I set alpha at point. I do not, essentially you're asking how does interval forecasting relate to quantile forecasting? If I set an alpha of 0.9 in my interval forecasting, which means I'm symmetrically trying to get between 0.95 and 0.05, if that helps. That would be the quantiles I would put in my quantile forecast. Yeah, I perhaps I did not understand this question completely, but from what I understand, yeah, that was it. Q3, can you estimate the calibration curve or probability integral? What's PIT? Sorry, I'm forgetting the full form of PIT. PIT histograms. Pardon me. From point forecasts. No, they're really all about the whole purpose of those diagrams are about probabilistic forecasting. So no. Finally, what's your opinion regarding training a model? Example, tuning a model based on the pinball loss for different values of tau. Selected models will be used for estimating real and optimistic scenarios. Yeah, no, that's that's a really good question. If I understand the correct question correctly, you're asking, can I have 2 separate models? One that's been trained to optimize 0.05, other that's been trained to optimize 0.9, and I will use them for 2 separate purposes. Absolutely. Actually, people do this like all the time. And I guess someone asked a clarifying question. So confidence interval is about quantifying the uncertainty in population parameters. Prediction interval is about uncertainty in population parameters plus other uncertainties. Yes, that's a TLDR. Yeah. All right. Thanks, guys. I hope you enjoyed it. I'm gonna share my actual PDF with Harsha, and then I'm sure he'll share it publicly.
Yeah.
And yeah, you can find me on LinkedIn. Just it's like the one guy with a big smile. That's me. And I'm always happy to talk with folks.
Yeah. Thank you very much
Okay.
for accepting our invitation to be our instructor today. It was really amazing presentation because it was so thorough, covering every bits and pieces from A to Z. That was
I'm glad.
really a perfect presentation. Thank you
Thank
very
you.
much.
All right. Bye, all.
Since we are running out of time, just let's wrap the session.
All right.
Thank you very much. Thank you guys for joining. See you. Take care.
Bye.